Hi, students. In the last lecture, we have discussed up to wave velocity, right? We have taken assumption that there is no loss of energy during the propagation. Then phase of the wave should be constant. Then we have taken derivative of the phase and making that equal to zero. From that, we got velocity of the wave, and this is also known as phase velocity. This is what we have discussed in the last class, right? Let us now continue. Next one is relation between particle velocity and wave velocity. See, we are knowing that suppose this is now string. Let us energy propagating along x-axis and oscillations are along y-axis. So when energy propagating along x-axis, particles oscillating along y-axis. So we want to connect now velocity of these particles with wave velocity. Okay. Now see what we are doing here. Differentiate equation 3. See equation 3 once. So this is now equation 3. Y equal to a sin omega t minus kx plus 5. So this is telling us wave is propagating in the positive x direction, right? Now differentiating this with respect to time. See here y represents displacement of the particle, right, along y-axis. If you differentiate with respect to time, that gives velocity of the particle. That gives velocity of the particle. Now see carefully here. So here we have taken velocity of the particle dou y by dou t. So this indicates we are taking the partial derivative dou y by dou t means. So we are differentiating with respect to t. So partial derivative means x is now constant. X is constant. Then see what we are getting? A omega cos omega t minus kx plus 5. Now let us understand what is the meaning of x is a constant. So here, when energy propagates along the string, that means when wave is propagating along the string, all particles in that string, they vibrate. I am repeating, when wave is propagating along x-axis, all particles in the string vibrate. So we are now focusing velocity of which particle that we have to mention. We have to mention velocity of which particle. Suppose we are taking now velocity of this particle. Let us say x equal to 1 centimeter. Take somewhere origin here. I am focusing one point, or you can say one particle whose x coordinate is 1 centimeter. That means now we are focusing velocity of this particle. This is oscillating like this. So the meaning of x is a constant. We are focusing one particular point on the string. Okay, right. Now see next one. Differentiate that equation with respect to x. And that gives us a slope dou y by dou x. Right. So differentiating with respect to x, that is giving us slope dou y by dou x. See what we got? Minus ak cos omega t minus kx plus 5. Right. Right. Now what we are doing is divide equation 4 with equation 5. Okay. So equation 4 is dou y by dou t. Right. Which is equal to velocity of the particle. So I have taken here small v for velocity of particle, capital V for velocity of wave. Okay. Right. Now see what we got here. velocity of particle is equal to velocity of wave into negative of slope, right? Velocity of the particle is equal to wave velocity into negative of slope. That is now relation between particle velocity and wave velocity. Let us see now how questions can be asked based on this result. Okay, right. Now see here. So we have taken y equal to a sine omega t minus kx. Okay, let us take this is the equation given. And for this equation, now see share. Let us take t equal to 0, then see what we get. Y equal to a sine minus kx. That means graph will be like this. We should be very careful how the shape of the string must be. Okay. Let us take this is now shape of the string when t equal to 0. Cross check once carefully. If I'm taking derivative of this, okay, derivative of this, then see what we get. Take dou y by dou x slope. That is, slope is, you can see at origin slope is negative. At origin slope is negative. Okay. Assume that velocity of the wave is along positive x-axis. Suppose question is given like this. Wave is propagating along positive x-axis. Take one point at origin, call it as J. Take one point somewhere here, call it as B. Take a point here, somewhere here, take it as C. This is a point D. Take a point here, that is now E. Right. Now we have to find direction of their velocities. Direction of their velocities. If I am taking point A, use now result carefully. Velocity of the particle is equal to velocity of wave into negative of slope. Right? At A, slope is negative. At A, slope is negative. So slope negative, negative of negative, positive. Okay. And it is given wave propagating along positive x direction. So V positive. So V positive, slope is negative, negative of negative, positive. This total value is positive. That means dou y by dou t is positive. I am repeating, at point A, slope is negative. So negative of negative, positive. V positive because wave is propagating along positive x-axis. So total is now positive. Means particle velocity is positive. So dou y by dou t is positive. That means y coordinate is increasing with time. So at origin, y coordinate is increasing. Its meaning is that that point is moving upwards. So direction of velocity of that particle is upwards. Okay. If you take now E, for E also same because slope is negative. That means you can say up to, suppose this point is F. For any point from A to F, I am repeating, for any point from A to F, slope is negative. V given positive. Therefore, for all these particles or for all these points, velocity is a positive. Means all these points in between A and F, they move upwards. And if you see from F2, F2 up to G. I'm taking top one G. From F to G, for all these points, slope is positive, means excluding F and G. At F, slope is 0. At G, slope is 0. Means for those 2 points, velocity is 0. So in between F and G, slope is positive. So slope positive means slope is positive, velocity negative. This total value is now negative. So for all points between F and G, for all points, direction of velocity is downwards. Right? See carefully. For all points between A and F, velocity upwards. For all points between F and G, velocity is downwards. Like this, we can expect problems basing on this result. Particle velocity is equal to a wave velocity into negative of slope. Okay. So this relation you have to remember. Right. Yeah. Next one. Speed of a transverse wave in a stretched string. Right. See carefully. Let us consider a shape on the string like this. This is now shape of the string. Okay. And velocity of the wave in the string, take it as it is to be. It is to be. So we want to find out speed of the transverse wave in the stretched string. See now what we are doing. Let us consider a frame. Consider a frame which has velocity same as that of the transverse wave. So we are taking, for example, there is a car which has a velocity same as that of the transverse wave. Same direction and same magnitude. So with respect to that car, that shape remains constant. I am repeating. If a person sees that shape from that car, okay, then that shape appears to be at rest. And remaining part of the string, that string appears to be moving in the shape like this, appears to moving. So this point we have to focus very carefully. So we have taken a car which has a velocity same as that of the transverse wave. Means now this shape appears to be stationary with respect to the car, and this string appears to move like this left side, and here following one curved path. Okay. So whenever a point or a particle or an object follows circular path, or I can say curved path, there must be centripetal force. I am repeating. Now this string follows a curved path like this. And to follow a curved path, there must be a centripetal force. So now we have to focus who is providing that centripetal force. Right. Let us see how to calculate that. Let us consider a small element on the string. On this shape, a small element. It is a very, very small. Let us amplify that and make a diagram separately. So this is now that element. To make it visible, we are drawing a little bit bigger. Suppose points P and Q. So this is now P and Q. You can see force is acting on PQ by left part of the string and right part of the string. They are pulling now, or you can say they are stretching PQ. That means tension is now here like this, tension T. And here also tension is now T. Okay. I am drawing here normals to that shape and they meet at center of curvature. Let us take now this angle. This is now 2 theta. Okay. Now see carefully. Take here angular bisector. Now take tension components. Right? Tension components. Then see what we get. Towards the center, we get tension components. See here shape I'm drawing once again. Tension T and tension T. This is T cos theta and this also T cos theta. These two cancelled, remaining T sin theta and T sin theta. Now these two are towards the center of the curvature. Therefore, net value it is 2T sin theta. So I have taken the first step, centripetal force. Centripetal force equal to mass into centripetal acceleration. Now centripetal force is the tension component is providing centripetal force. So 2T sin theta is equal to mass. Mass is, it is nothing but arc length, right? Arc length is R into angle is 2 theta. I am repeating, arc length is R into 2 theta. So mu is mass per unit length. So mu into length of the arc. That gives mass of that length. Right? M into V square by R. Now here we are taking assumption that angle is very very small. Theta value very small. When theta is very small, sine theta approximately equal to theta. Then theta and here theta gets cancelled. 2 and 2 gets cancelled. Right? R and R gets cancelled. Remaining is now V equal to root of T by mu. Okay. This is now expression for speed of a transverse wave in a stretched string. Okay. Where mu is mass per unit length or linear mass density. Right. Let us now solve a problem basing on this. So it is given a heavy but uniform rope of length L is suspended from a ceiling. Right. The velocity of a transverse wave traveling on the string as a function of the distance from the lower end. Next, if the rope is given a sudden sideways jerk at the bottom, how long will it take for the pulse to reach the ceiling? And last one, a particle is dropped from the ceiling at the instant the bottom end is given the jerk. Where will the particle meet the pulse? This is now question. And this question is taken from HCV, HC Verma. See the first one, what we have to calculate. Velocity of transverse wave, right? Right. Let us make a diagram here. This is now string which is a hanging from a ceiling. He's asking as a function of distance from the free end. Let us take distance x from the free end. Now we have to focus, see how to start the problem. We have to find velocity of transverse wave. And for that expression is V equal to root of T by mu. T is now tension. Now, when a rope is hanging freely, which has some mass, tension at that point will be equal to weight of the rope below that point. I am repeating. When a rope is hanging which has mass, tension at a point is equal to weight of the rope below that point. That means if I'm taking mu is now, mu is mass per unit length, mu into x gives mass. Okay. So here we have taken now mu into x, that is mass into g, mg. That is now tension. That is now tension. So T by mu. Okay. So mu gets cancelled. Remaining is now root of xg. So from this we can say speed of the transverse wave increases as it moves upwards. It is not a constant. Okay. Right. Now we have to calculate how long the pulse takes to reach the ceiling. So here what we are doing is we are vibrating this bottom end like this, okay, in this way. Vibrate horizontally. Then a pulse will be produced on this, which propagates upwards, right? So we have to find how long this pulse takes to reach ceiling. Yeah. And here we got velocity is now variable. In such a case, we have to take integration. So let us see first of all, what is acceleration? Acceleration equal to. So we want to connect acceleration, velocity and position. Okay. Relation is A equal to V dV by dx. Right. So in the place of V, root of xg, dV by dx, root of xg, 1 by 2 root xg. Right. So root x, that's cancel. It is equal to g by 2. That means the pulse is moving with a constant acceleration. I am repeating, the pulse is moving up with a constant acceleration. That is g by 2. Since the acceleration is a constant, now we can write s equal to half a t square. S equal to half a t square. Okay. Now in that S equal to length of the spring that we have taken, it is L, half a t square. Why half a t square means when x equal to 0, velocity equal to 0. So it starts from rest. So S equal to ut plus half a t square, u value 0. That's why it is simply half a t square, right? And from that, in the place of a, right, g by 2, then we get t equal to 2 root of L by g. Like this, we can solve the problem. Okay. Suppose if they ask, what is average velocity? So what we can do is here, since acceleration is a constant, average velocity equal to initial velocity plus final velocity by 2. See carefully the value how much? Average velocity. Initial velocity 0. Final velocity root of Lg, because expression is root of xg by 2. Initial value plus final value by 2. That is now average velocity. Okay. So like this, we can expect any question based on this problem. Let's see what we have to calculate in that. So we have finished the first part in this one, right? Next, second part, it is also over. Next, third part. A particle is dropped from the ceiling. At the instant, the bottom end is given the jerk. Where will the particle meet the pulse? Right? Now see how to solve it. So question is given that it is a body is a drop, right, from here. And this pulse is moving upwards, right? Here you can observe the body which is a drop has a constant acceleration, that is g downwards. and this pulse is moving up with a constant acceleration g by 2 upwards. So here what we can do is we can take relative velocity. Let's see what we can say. U relative. Initially relative velocity. Body dropped. Zero velocity. And for the pulse, initially velocity equal to 0. Therefore, 0 minus 0. It is 0. Next, coming to relative acceleration. One is g upwards, sorry, g downwards. Second one, g by 2 upwards. So relative value, g plus g by 2. It is 3g by 2. And we have to focus now relative displacement, that is equal to L. Okay. So if you are taken now with respect to the dropped body, pulse is moving upwards with acceleration 3g by 2. I am repeating. If you take velocity of the pulse, velocity of the pulse with respect to dropped body, its velocity equal to 0 initially. Its acceleration is 3g by 2 upwards. Displacement equal to L. So we can write now equation. Equation is S equal to half a t square. S relative, that is L, half a value 3g by 2 into t square. Right? From this we get the value of t. So t value how much? 2 to so 4, that is now 2 root of L by 3g. This is now time taken by the pulse to reach that dropped body. Okay. This is regarding that problem.